Calculus. I bet for a lot of you, just hearing that word brings up a cold sweat. It's got this reputation, right? The final boss of high school math, something only geniuses can handle. But what if I told you that's not really the whole story? What if, at its heart, calculus is just a powerful toolbox built on two, surprisingly simple ideas? Okay, let's actually dive in and see for ourselves. So let's just ask it outright. Is it really that scary? The intimidation factor is totally real. I get it. But the truth is, calculus wasn't invented just to be complicated. Nope. It was created to solve very specific problems that all the other math we had, well, it just couldn't touch. So today, we're going to strip away all that fear and just look at the two big fundamental questions that calculus was born to answer.
And that brings us right to our first major hurdle, the measurement challenge. This is all about finding the size of stuff. Now, for some objects, this is incredibly simple.
I mean, look at the difference here. On one side, you've got your friendly neighborhood shapes like rectangles, circles, and triangles. Finding the area? Super easy. We have simple, reliable formulas for those, right? Length times width, pi r squared, we know this stuff. But then, you look at that shape on the right. It's all curvy and unpredictable. There's just no simple formula for that.
Yeah, exactly. How in the world do you find the area of that thing? You can't just plug numbers into some formula you learned in middle school. Before calculus came along, your only real option was to guess, Maybe try to draw a bunch of tiny squares inside and count them up, but it would always be an estimate. And that is the absolute key. An estimate just doesn't cut it when you're an engineer designing an airplane wing or a scientist modeling a magnetic field. In the real world, precision is everything. You can't be close enough. You need the exact answer. So how do we get there? Well, this is where calculus steps in with its first totally brilliant solution, the integral. It's the tool specifically designed to conquer this exact measurement problem. Okay, so the integral, that's that long kind of stretchy S symbol. It's basically a method for finding the perfect exact area of a complex shape. And the big idea behind it is actually beautiful. It slices that weird shape into an infinite number of impossibly thin little rectangles, and then adds all their areas up perfectly. No guesswork involved. So how does this actually work? Let's say the curvy top of our shape is described by a simple function, something like x squared. To find the area, you don't do some crazy geometry. You just follow a simple recipe. Step 1, you take the exponent, which is 2, and add 1 to it. So now it's x to the third. Step 2, you just divide by that new number, 3. That's it. You've got a brand new formula, x cubed over 3, that gives you the exact area between any 2 points. It's just a procedure, a set of rules, not some kind of dark magic. Okay, problem 1 solved. The integral lets us measure the area of all kinds of weird shapes. But that's only half the story. The second huge challenge that calculus takes on is what I like to call the right now problem. It's about measuring things at a single instant.
Think about it like this. If you have a straight line on a graph and you want to know how steep it is, that's easy, right? We all learn this. You just pick 2 points and do the whole rise over run thing to find the slope. That tells you the average change over a certain distance.
But what about a curve? The steepness, the slope is changing all the time. At one point, it might be climbing really steeply, and just a little bit later, it might be almost totally flat. So how do you measure the slope at one single, precise, instantaneous moment? Rise over run totally fails us here because you only have 1 point to work with, not 2. And why should you care? Well, because almost everything interesting in the world is constantly changing. The price of a stock doesn't just have an average for the day, it has a price right now. A scientist testing a new medicine needs to know the exact moment it hits its peak effectiveness. We need to understand not just how things change over time, but the speed of that change at any given instant. And for this problem, you guessed it, calculus gives us its second powerhouse tool, the derivative. The derivative is, for all intents and purposes, a slope-finding machine. You give it the function for your curve, and it spits back a new function that tells you the exact instantaneous slope at any single point you want to pick. It's the tool that lets us analyze change with perfect, pinpoint precision. There's this great quote that just gets to the absolute heart of all of this. Calculus helps us determine the exact answer, not an estimate. And that's really the theme, isn't it? Whether we're talking about area with integrals or rates of change with derivatives, it all comes down to the same thing. Calculus is the leap from making a pretty good guess to knowing the exact, provable truth. So there you have it, the two core pillars of calculus.
It's not 1,000 different complicated ideas all tangled together. It's really just two big ideas with, well, pretty much infinite applications.
So let's just break it down one last time to make sure it sticks. First, we had the problem of finding the area of weird shapes. For that, calculus gave us the integral, which works by adding up infinite tiny slices. Then we had the problem of finding the rate of change at one single moment. For that, we got the derivative, which finds the slope at one exact point. Two huge problems, two brilliant tools.
And that is fundamentally it. Seriously, all those homework problems, all those symbols, all those late nights studying for a first-year calculus class, they're really just about learning all the different rules and techniques for using these two incredible tools on trickier and trickier problems. But you now understand the why behind the entire subject.
So you see, calculus isn't just a bunch of abstract math. It's literally the language we use to describe a world that is always in motion, a world that is constantly changing. Everything from the orbit of a planet to the flow of traffic to how an idea spreads on the internet. So the only real question left is, what will you use it to describe?